So thank you all for coming, especially when there's such a parallel colloquium, which sounds very interesting. I personally would have wanted to go to also the colloquium, so I appreciate your presence here. So I'm Adrian Poe. I'm now a Pappalardo fellow here at MIT, and today we're basically talking about topological materials. And in particular, we want to make a connection to what we learn typically in high school and see how this modification of what we learned in high school can naturally explain this kind of mysterious subject of topological materials. So let me spend maybe 2 minutes giving you a super quick review of what we mean by topology. So at least when I was a kid, I heard this. I have no idea what this is, but I knew that's supposed to be an interesting and exciting topic. So the first introduction I had to this idea was that you take an orange and you take a bagel, and then they're topologically distinct. And as a 5-year-old, I would say, like, come on, this is super obvious. Like, why should I try to even compare them and think of them as ever being the same or different? So of course, as I mature a little bit, I realized there's a lot more content to this simple sounding statement. So in topology, we usually try to think about smooth deformations. And in this particular case, we think of the surfaces of these objects, and essentially the key invariant here would be the number of holes. So this equality or inequality, you should read it as saying there's no hole here, and then there's one hole here and also one hole there. So in this sense, these are topological equivalent in the sense of you can maybe abstract it and try to deform the surface. So that is fine. And now we take this classical introduction of what we mean by topological distinctions, and we try to put in materials to that. And the surprising conclusion is that if we try to do the same kind of argument, we'll say something like diamond is different from whatever black object on the left here. So any idea what that is? No. So this is something kind of boring and also interesting in physics. So this is just graphite. So basically, if you try to think about topological materials, then we'll say maybe just diamond and graphite. They are both formed by only carbons in different arrangements, but then they're really topologically distinct. And in particular, for physicists, or at least for my purpose today, I will claim that the right-hand side is more interesting than the left. But if you're going to give one of these to me, then by far, please give me diamond. So that's really like a very high-level introduction to topological materials. And let's see if we can do it a bit more properly. So there's a sense in which there are topological materials proper. So there's a pretty profound mathematical theory behind all of these. I've taken some snapshots of equations from this seminal paper by Fried and Moore back in 2013. Don't quiz me on what this means, because I honestly don't know that much about all these mathematical formalism. But then you can see that this is a pretty rich and deep subject in this regard. And also, there's also another aspect to this problem, which is to ask, where can we actually find topological materials? Are they only some equations that you can try to write down and imagine being or imagine classifying? Or you can actually find them and synthesize them and measure them in a lab. So to find them, we basically have to combine basically the periodic table. So there are more than 100 elements here, but maybe what we care about would be roughly 50 of them. That's only part of the story, because that only tells the elements. And then you have to try to combine them into some actual materials or into some actual crystalline structures. And in 3 dimensions, it's known that there are 230 space groups, if you don't worry about time reversal symmetry breaking. So you combine the elements in different ways, then easily you can be convinced that there are easily more than 10,000 combinations. In fact, there may be even 100,000 combinations. So we would want to find something kind of exotic out of all these combinations. And the question I want to answer today is how we can try to achieve this task in a systematic way. So in a sense, we can summarize this whole field of topological materials as saying you have some very sophisticated mathematics, and they meet some very complicated chemistry. So it seems hard to actually make any progress. And today, I will try to tell you that maybe this is not quite the full story here. And the plan today is that I'll first try to give you a more physical picture for understanding these subjects, or these objects that we call topological materials. And then I will try to convince you that by using this pretty simple physical picture, we can actually go find them and kind of bypass all these complicated mathematics as well as chemistry. So I will go back to what I promised, which is that we will try to motivate the entire discussions starting from what we learned in high school chemistry. So I'm not sure if this is universally true over the world, but at least when I was in high school in chemistry, I was taught that basically you get insulators for one reason, which is that the electrons are localized in space. So there are finer distinctions. You can say maybe I have ionic compound, in which case some elements want to lose an electron and donate it to some other else. And at the end of the day, the electrons is localized to these other atoms, and therefore they form ions. And that's one form of forming a stable chemical bond, or a stable bond between the atoms. The other possibility is that you have some covalent compounds. So it's not as simple as saying you just take an electron away from someone and then donate it to someone else. But at the end of the day, you still try to localize all electrons to these chemical bonds that are between the atoms. So in both cases, it's important that your electrons are really localized in real space. So I really know that the electrons are either at, say, the green dots here, or they are really localized to the bonds here. So that's really what we learned in, or what I learned in high school chemistry about how we can get insulators. And this particular form of insulators, we can actually model it quite easily. So I've prepared a little gadget here. So I've just a plain coffee mug here. And this I would think of as my atomic or interatomic orbitals. So basically, it's like an energy trap. And then now I've also prepared something which is it's just a rubber band ball. But whatever you want to call it, it's just like a small ball, piece of small marble, if you like. So I just take this electron, or what I would call electron, and I try to put it into this energy well. So now let's imagine what happens if I try to tilt it a little bit or shake it. It's not going to escape, right? Because there's this energy barrier. It's not going to move out of it. So now, of course, if I tilt it all the way down, then this can fall out. But then we know that basically in a crystal, what happens is that your particle-like electrons are trapped in these kind of potential wells. And that's why when we try to perturb it by electric field or whatnot, they don't quite move and we don't get conduction. So now let me declare that I actually lied to you. My model for electron is actually quantum mechanical. So I just take the same mug here, and because it's a quantum mechanical electron, they don't have to stay where it is. So what happened? So for classical objects, we know that they have to get stuck in where we put them as long as there's an energy barrier. But then electrons are really quantum mechanical. So because of that, there's this effect of tunneling, and my electrons don't have to stay inside here because I declare it's a quantum model. So in fact, during this course of talking about it, it has tunneled away, and I would suggest that you search your pocket. Maybe it will be in one of yours. So can any one of you find my electrons? Anyone? I'm getting a bit nervous here. Is it actually still here, or has disappeared? Oh, not surprisingly, Neil has it. So what happened was that, of course, this is a symposium in his honor. So, but you can also say that I've designed my Hamiltonian very carefully so that there's a resonance of amplitude and it got tunneled there. So jokes aside, the main point here is that if I do think about the fact that electrons are quantum mechanical, they don't really want to stay where they are. So if this is like a wave function for my quantum cat, at time being 0, maybe it's exactly within the trap, and there's no probability of finding outside. But as time moves on, it can actually spread a little bit, and this will be, at later times, there will be a non-zero probability of finding it out there. So this is really how your quantum particle can escape from this kind of potential well. And if now we try to think about this as something like a quantum electron, which is trapped inside a crystal, so there are many equivalent potential wells. So maybe I can try to first trap it in this first well, and it's kind of cozy down there. It's not going to move, except that it can actually explore its neighborhood, and it will find that all the other wells are equally cozy. So there's no reason why it will want to stay trapped there. So we now have a pretty big problem, because as long as we realize that electrons are really quantum mechanical, it's actually very hard to trap them. They can really just explore the surrounding and then go to other wells. So the problem coming from the wave nature of electrons is that if we cannot really trap a quantum electron, then how do we ever get any insulators? So this simple picture doesn't seem to quite work with quantum mechanics. So let me try to explain to you how that actually works in reality, or at least we know for sure that we do get insulators in the world. So the solution is to allude to this idea of quantum interference. And let me try to explain that to you with some analogy. So I have here that something that I've termed Prudent Piggy quantum fund. Maybe I'll actually start this fund after 30 years or something like that. But this is, of course, imaginary. But then the rule of this fund is as follows. So this is a 1-year investment, and every day you have to put in a quantum dollar. But then being quantum, the face of the dollar you put on day D would be something like e to the I 2 pi d over 365. And that's not variable leap years. So this is the phase of the quantum dollar you put in. And the return, I guarantee, will be 10 times the amount after day 365. Or if you like, I can even put 10 million there or 10 billion there because it doesn't matter. So what happens is that with these quantum dollars, even though it seems like you're putting in something into your piggy bank every day, they destructively interfere such that at the end of the day, you have put in nothing in it. Therefore, I'm not going to pay you anything. But that's at least prudent. I'm not trying to take money away from you. But you see that this is how, with quantum mechanics, you can try to leverage this idea of interference and have some counterintuitive effect in which you don't really get the transfer you're imagining. So this is what really happens in these kind of quantum insulators. You can picture that each of these waves is like a single electron. And each of them is delocalized in space. This is just because they are wave-like and they don't really want that the natural eigenstates are not going to be localized in a crystal. But then when you have all these electrons all together, even though each of them seems to be moving from the left to right, because of this interfering effect over all of them, at the end of the day, you don't really transfer any charges from left to the right. So this is how you can get an insulator, even with quantum mechanics. And that's of course not what is taught in high school, at least not in my high school. But then we know that typically what you learned when you were small, they are usually true or they are good approximations to truth. So we should ask, how do we reconcile these two pictures of a classical insulator in which you think of particle-like electrons that are trapped in potential wells in real space, versus this kind of delicate quantum mechanical interference effect of getting an insulator. So to the extent that quantum mechanics is more fundamental, we know that you should be able to always start with this classical limit, add quantum mechanics, and then derive this kind of discussion. So that should be fine. Let me not do it here. But the interesting question is to ask if understanding quantum mechanics is going to give us something extra, which is to say, if it is true or not that there can be some quantum mechanical insulators that are inherently wave-like, and there's no way to think of it in terms of these classical pictures of particle-like electrons trapped in real space. And let me not keep you in suspense and just tell you the answer, which is, indeed, this set of insulator is richer than the classical pictures we had, or the classical pictures taught in high school. And precisely this type of insulators that are quantum mechanical without a classical explanation, they are what we will call topological materials. So now this is, in a way, a physical shortcut to all these mathematical formulation of what exactly is a vector bundle and non-trivial deformation of that. But we just have this simple physical picture. You give me an insulator. I just want to ask if I can relabel my degrees of freedom to go back to this classical picture or not. So you may ask, like, why should I try to understand these kind of maybe equivalent discussions of a system? And one interesting property of these quantum insulators are the response to the presence of a boundary. So let's first think about this classical setup. All my electrons are trapped in real space, and I impose a boundary. What happens is that the right-hand side of it is all gone, and the electrons that are localized near the boundary, they actually may not care that much about it. So they'll just say, OK, bye, but then they're not going to do anything. So this will remain an insulator even at the boundary in this kind of pictures. But let's try to do the same with this wave-like picture of a quantum insulator, and you just impose a boundary. And if you trust me that the insulating behavior comes from some very delicate quantum interference, the simple imposition of a boundary is going to really mess up what they want to do here. And if they could speak, I hypothesize that they will panic, sing, and shout, and say they're free. So basically, they were insulating only because of this interference effect. And by imposing a boundary, I'm really stopping them from doing their very delicate quantum interference. And because of that, then we see that it's kind of natural for the boundary to become conducting. So of course, we can have much sharper statement about it, but let me not go into the details, but just tell you what is the signature of these kind of topological materials. So in the interior of your sample, it could be just a plain, boring-looking insulator. But then at the boundary, because of the non-trivial nature of the material, it's actually going to be conducting. And you can even try to maybe chip away the boundary of it, and you'll think, aha, I've basically stopped it from trying to be conducting. But then for the fact that it's a topological surface states, what that means is that even if you try to chip away the first layer, the layer immediately underneath will start becoming conducting. So this is really the non-trivial property here. And we can ask how you might try to use it for something that is like functional, or maybe not in 10 years, but maybe in 30 years. So this is a very simple cartoon. Maybe what you can imagine is that I can have some device, and I can arrange my conduction channels such that it's going from up to top, because there's a topological interior and there's a trivial counterpart outside. And I can imagine just in situ tuning some parameters and then changing how they arranged, and maybe change my condition from going vertically to horizontally. So this is just one very simple cartoon picture. But we see that as long as you have some new ways of functionalizing your materials, and this could be useful for technological purposes. But then, to really move our theory to that step, we need to actually give real materials candidates that will realize all these interesting physics. So we should ask, how does this picture of understanding corrections to high school chemistry can help us find topological materials? And I've shown this picture many times already. The main take home here is that we want to focus on this side, which are insulators that are inherently quantum mechanical and doesn't have any classical description. But this is too schematic. In theoretical physics, we really want something that I can sit down and compute. So the question here is to answer is to how we can take this picture and make it more concrete and give some computable or falsifiable predictions. So this is getting a little technical, and let me not go into all the details. But let me just tell you that if you try to think about the symmetry data of this particular diagram, it becomes something that is very easy to compute for essentially all possible settings, like 230 space groups, or if you like magnetic settings, you have 1,651 magnetic space groups. Those are all tamed within this framework. And this is more like a slide just for the experts. The key idea is that we want to first characterize how electrons in the crystal can respect crystalline symmetries. And then you study their representations, but the representations are discrete, like maybe spin 0, spin half, spin 1, so on and so forth. So the allowed representations in our setting is also discrete. They're like groups of integers. And then you can try to systematically enumerate all the possible representations and then identify the trivial subset. And then now there's a mathematical notion of quotienting out some subgroup, and then you'll get the interesting bits that are left behind. So more pictorially, this is what is really happening in this framework. So first, we'll start with the general set of all possible insulators or band structures, more technically. Then they basically form some copies of integers, like c to some power. So this d is just a large number in general, but then here I've shown something like a two-dimensional example. And what we can do is to translate this simple diagram of mismatch into this language, and you can identify a trivial subgroup of it. Now, this kind of mathematical objects have some nice properties that you can identify some bases, and in particular, you can basically equate any possible material as something like a vector in this space. So after all these developments, at the end of the day, what you distill out of it is that you can put any possible material, you can try to find its coordinate in this chart, and you just do a simple diagnostic. You ask if it's sitting on the white dots or a red dots. If it's a white dot, then maybe it's a trivial material, and maybe we're not interested in that. But as long as your material sits on a red dot, that is guaranteed that it's going to be topologically interesting. And more technically, this mismatch can be exposed as a quotient group because between this larger group of general objects and the trivial subgroup. And this is a result we derived. Maybe I could call it a theorem, but it's probably not really worth that name. But anyhow, so what we derived is that you can try to compute this kind of object for all possible 1,651 magnetic space groups with or without spin-orbit coupling. Just do it. And what we can prove is that it's going to be a finite abelian group. So the abelian part is automatic. What is quite surprising is that it's finite. So there's some interpretation behind these, but at the end of the day, what we know is that basically any material has an address in this kind of formulation. A trivial insulator, the address must be 0 under all these subgroups. But then anything which doesn't have a completely 0 address, they're guaranteed to be topological. And in the interest of time, I've done the calculation. This is for all the 1,651 magnetic space groups. And there are just 20 more pages of this calculation. So let me now spend the remaining 5 days talking about each entry here, except that you will all leave. So let me not do it. So just trust me, this has been done. And the more interesting thing is to ask how we are going to use this kind of slightly abstract framework to find real materials. And this is what we've done in this series of papers, and also there are contemporary works by other groups. So these are new families of topological insulators or topological crystalline insulators that are maybe messy from a chemistry point of view, or maybe surprising in the chemistry point of view. But then by this formalism, we can very easily identify all of them as being topologically interesting. And it's not, our formalism is not limited to only insulators, but it also works for semi-metals, for instance. And this is just some snapshot, and we just have, again, tables of materials that we predicted, and we found like thousands of them just by using this framework. So let me now summarize. The main take home is that this interesting idea of topological materials, we should really think of it as the more general possibility of insulators you get from quantum mechanics. And there's a mismatch between the general framework versus what we learned in high school, which is a classical picture. And a suitable abstraction of this really simple physical picture actually allows us to predict thousands of topological materials. And the next step is, of course, to convince our experimental colleagues to really go verify or falsify our predictions. And with that, I'll conclude by acknowledging my collaborators. These are people with whom I work on the more theoretical side of the development, and also people who did the actual and initial calculations. And for those of you who really pay a lot of attention to this slide, you'll see that none of them are actually at MIT. So you ask, what happens at MIT? So at MIT, I've been doing something which is maybe related, but quite orthogonal to zeroth order. So on the one hand, we've been trying to understand the system of twisted bilayer graphene, which has been experimentally discovered as being very interesting with both insulators and superconductors here locally in Pablo's group. So the work done at MIT for understanding this problem is with Santil, Yahui, and Adrian. And on the right, I've also been trying to revisit some of my old interests, which is about how you can have interesting quantum dynamics in disordered system. So that's very different from all these crystalline and stuff like that, but then it's quite interesting to also think about all these different problems. And I should end by saying, as a postdoc, it's a privilege to be able to work on these different things in different domains. Some of them I don't even have any expertise on, so I may just fail in finding anything interesting. But I really thank Neil and Jane for their support. Because of this Pappalardo fellowship, I'm allowed to do whatever I want and maybe find something that is out of the blue. So thank you.
Questions? Front row? No? Sarah?
So after you found these thousands and thousands of interesting topological materials, what's the next step? I understand you're probably not doing it, but how does someone else take those and work through the list to find something that's maybe practically implementable?
Right. So what is interesting is that in this field, you usually start by finding some representative in the family, for instance, and then you can now try to improve on that. So what people have, so basically there's a lot of experimental progress on finding materials before us, but then they combine like physical as well as chemical insight, and they found maybe a few families. So what we try to do here is to say there's an orthogonal perspective, and you can find thousands of different other families. And the next step would be to naturally, like for say a chemist, maybe they will try to grow whatever that is easiest within the lab, so with maximal overlap with whatever their techniques are. And then they can try to characterize it and hope to improve it. And some of these may be toxic to start with. Maybe you want to find a non-toxic representative of some of them. And down the road, we really hope that this can be like the semiconductors in 100 years, for instance. So they will hopefully really become part of the technology, but then it's not going to happen within 20 years, I guess, like very a conservative estimate.
But of the thousands you have, there has to be a much, much smaller number of families that are so close to each other.
That is right. That is right.
Do any individuals stand out yet?
So some of these, what we predict are maybe surprising from that kind of perspective, at least from people I've talked with. Say, for instance, this kind of messy thing that usually like first ruled out from any sensible person trying to predict a material. And what we found is that because we use this other kind of perspective, then we'll naturally pick this up and say this may be interesting. So really these are belonging to families that are otherwise not even considered in a more conventional approach. So we're really finding new sorts of families, and then you can try to build on these and see if we can improve the material qualities.
But
and also some of these may be different variants of topological materials. There are actually many kinds. And these are maybe the more well-known kinds, but there are many other kinds, and there's always a question of whether you can find a representative of each of the possible kinds. So that's also something that we can achieve within this framework.
Are you able to post-stick ones that have already been found?
Yeah. If not, we'll have trouble.
How are you doing with that?
So we basically, I should say there's some limitation to our method. So it's more like a snapshot. So I was actually kind of careful in drawing this. So the red ones are topological, but then some of them may look identical from the trivial ones. That's why I show the red dots as being overlaid with the white dots. So it's possible that you have topological materials that are missed from this diagnostic. Mm-hmm. So it's like an indicator. It's not like a full classification. So some of the known materials just happen to sit in these spots, then we're going to miss them. But then for all those that should be visible to us when we just rediscover them as a sanity check.
Pablo.
So all this calculation is based on single particle physics,
That's
right?
right.
So if you introduce interactions, or many of those materials, interactions may play a significant role. Do you expect to alter the topological properties?
Right. So to the extent that you still have like a basically mean field description of the material, it doesn't matter. There's always a theoretical question of whether interaction, however that's small, can change the topological classification of your materials. And for whatever we talk about here in, say, technically class A2 in 3D, that doesn't happen, basically, except for some mirror churn reduction that is not very likely. But then we have interesting candidates we can talk offline. We've now found maybe some 2D materials that actually realize this interaction reduction. So that would be the more interesting thing, because interaction will actually do something. Yeah.
All right.
Could this eventually help to find high TC superconductors?
I would very much want to say yes, but I'm just being super optimistic. So my understanding is that finding high TC, there has been many approaches to do it systematically. But at the end of the day, the nature doesn't seem to work that way. So many of the high TC materials are found with some insights that may not even be right, but then you just do it in the lab and it turns out to be high TC. So that may be the right way to go for finding high TC materials. Yeah.
Any more? Richard.
Can you make any statements regarding what fraction of possible materials are topological?
Yeah, that's an interesting question. So before we do these studies as well as like contemporary works, it seems like topological stuff is supposed to be exotic. Maybe they're less than 1% of that. That's not quite true. It turns out it's roughly on the order of 20 to 30% of known materials are actually topological in one way or the other. But they may have very, very different qualities. Like you want to call it an insulator when it's like a very metallic thing due to compensated pockets and stuff like that. But then if you use a very relaxed criterion, some 20% of known materials are just topological in one way or the other. Yeah, this is kind of surprising. It's like saying all these people who do these synthesis, they have a very good hunch of what is actually interesting. They have a fairly success rate on like synthesizing topological materials even without knowing that.
Okay, let's thank Adrian again.